We have three main topics that we're going to be looking at, okay? I know it's a lot more than just three, but I've generalized them into radical reactions, aromatics, and the reactions of carbonyls and epoxides, okay? So I know you guys may not be totally, I guess, not familiar, but you guys might not necessarily remember too much of what we did for radical reactions. The purpose of this first part will be kind of refreshing what you need to know, okay? So yeah, before we get started, I'll just let you guys know that this will focus more heavily on allylic and benzylic bromination rather than just alkyl bromination. So for those of you who are familiar with Dr. Falzone's class at the end of last semester, he talked a lot about, how to get different stereoisomers, regioisomers, and all that. I won't really have time to go over doing all those problems, but there's a lot of practice in the pilot set that you can go and then use to refresh on that. But we're mainly going to be talking about allylic and benzylic bromination since those are going to be the most useful for synthesis. All right, so let's go ahead and get started with our first topic, which is our radical reactions. Okay, so as I mentioned, the big type of reaction that we had previously was our bromination or our halogenation of just alkyl groups, right? So let's say I had some sort of a cyclohexane. I went ahead and I denoted one of the protons that we have here, because we can go ahead and then use some sort of a reagent to go and then to replace it with some sort of a halogen like bromine. And in this case, the halogen that we could potentially be using here would be Br2 along with H nu, which just represents UV light. Okay, so that UV light or heat will be present throughout the different types of reactions that we're going to be looking at, but now we're going to be dealing particularly more with trying to halogenate in places that have better radical regioselectivity. And that's the whole premise behind allylic bromination and benzylic bromination. Okay, so let's go ahead and then look at allylic bromination first, because that one has a little bit more depth of problems associated with them. Okay, so for allylic bromination, right, the reagents are going to be very similar. So let's say I had instead of a cyclohexane, I had a cyclohexene. Right, I'm going to go and then take a proton that is in the allylic position, right? That's where we go ahead and then form an allylic radical, which is stable. And we can go and then replace it with some sort of a halogen, which in this case, or all the cases I'll be doing will be with bromine, but you could certainly do it with chlorine as well. Now, to do this, you need to be careful with the concentration of the reagents that you used. So notice that previously, if my iPad lets me scroll up, previously we used bromide. We can use pretty much infinite concentration because if you think about it, wherever you brominate, it's going to be the same place. But here you want to try and limit the over halogenation that is possible. So in that case, you would have to use NBS, which is a lower concentration of bromide. Okay, remember that. So in case you forget that, remember that this can be reduced to lower concentrations with NBS. Oops, sorry. And that will be primarily what you will be using for your allylic and your benzylic bromination. Okay. Now, allylic bromination, what can potentially make allylic bromination a little trickier for us? That's the fact that we can potentially have multiple allylic positions, right? Not as much multiple benzylic positions unless you have multiple substituents on your benzene rings, but multiple allylic positions can allow us to get different regioisomers. So let's look at an example of that. Let's say I had a compound that looks like this. Okay, and I want to go and then find the different possible places I can go and then add a bromine to the allylic position. First, we want to notice the different possible allylic positions that we have. Okay, we see that we have one allylic position over here. We have one allylic position over here, and we have one allylic position down here. Okay, so that's three totally different allylic positions, giving us three different radicals. So let's go ahead and then draw those out. So now our blue one would end up looking like this. Pop quiz for you guys. What is the hybridization of a radical?
sp2.
sp2, right. And if you're sp2, you're planar. So that's why I noticed that even though this guy is originally wedged over here, looks like my Apple Pencil's dying. Notice that because even though it's originally wedged in the starting material, I now drew it planar because that carbon that once held that wedged methyl group is now going to be planar. Please make sure that you're not drawing anything that's not planar whenever you have an sp2 hybridized carbon. Okay, wait 5 more seconds for my Apple Pencil. 5, 4, 3, 2, 1. All right, cool. That was not 5 seconds, but whatever. Okay, now let's go ahead and then look at the other position. Okay, the other radical is still sp2 hybridized, but we don't have to worry about it that much because there's no induced stereochem on there. And then, of course, there is that third one down there, which we also have to worry about as well. So these are your 3 allylic radicals that you could potentially get. Now, if you have an allylic radical, what can we do with that radical? Anything that's allylic?
Resonate.
Resonate, very good. So we have different possible resonance structures. So remember that with these resonance structures, we want to use our single-headed arrows. And when you have a single-headed arrow, that represents you're only moving 1 electron. So we're moving the electrons from this radical and from this double bond, okay? So that's 3 electrons that you have to move total. That means that you're gonna have 3 resonance arrows for this case. So I can go and then move 1 electron here, move 1 electron here, and move 1 electron here. So that goes and then gives me another structure that looks like this. Notice that everything that's in that pi system is sp2, which defines conjugation, which is good. Okay, now let's go ahead and then look at this next one right here. Okay, deposit electrons here, here, and here. We end up getting another radical here. This time that double bond is going to be outside of the ring. And then last but certainly not least, we can go and then move these electrons over here. And then now we get our double bond at that position, okay? So this tells us that we have 6 different places that we can put our radical. Okay, that means that once we have a radical there, we can go and then replace all those positions with a bromide. So we can go ahead and do that. I'm going to be extra lazy and just copy and paste everything here. Let me move this here. Here, I got you. I'll move this up here and then I'll give myself some space down here. So now every radical now becomes a bromine after that bromination. So now we end up getting so now we get a bromine over here at this position. We get a bromine at this position, and we get a bromine at this position. Okay, and then we do the same thing for the other resonance structures. Okay, you got a bromine at this allylic position. You got a bromine at this allylic position. And get a bromine at this allylic position. Okay, so that means that considering this, we get a total of 6 different regioisomer products. Okay, we're lucky here that all 6 resonance structures denote a different regioisomer. However, in many cases, you'll need to double check because sometimes you actually do end up seeing that you might have 2 identical resonance structures. And in that case, of course, you don't want to consider those 2 as different ones, but rather the same one. Okay, so these would be the 6 possible regioisomers that we have for this. Okay, and that's pretty much what you need to know for allylic bromination. Now, if I were to sit here and ask you, which of these is likely to be your most thermodynamically favorable product, which one would you say it is?
Top right.
And why would you say the top right?
It has the most substituted double bond.
Excellent, very good. So we could say that this guy right here is the most thermodynamically favorable. And that's because of the fact that this double bond, if you consider it, it has 1, 2, 3, 4 substituents on it. Okay, there are multiple kinetic products here, but you're less likely to be asked to interpret that. Okay, the thermodynamic one is usually the one that's going to be the most easily found. Okay, any questions about allylic bromination? All right, and then stemming off of allylic bromination is benzylic bromination. Okay, which is just bromination in the benzylic position. Okay, now I'm going to show you exactly how this looks like, and I'll show you some pet peeves of mine that, as a grade, I'm not grading this semester, but I've graded before, and as a grader, this is stuff that that graders do not want to be seeing because you lose points, and I'm sure you don't want to lose points. Okay, so when I'm doing benzylic bromination, what I want to do is to take a hydrogen that is on the benzylic position and then replace that through a radical intermediate with a bromide. Okay, so this position right here, immediately alpha to the benzene ring, is called the benzylic position. Okay, this reaction is not possible if you do not have anything in the benzylic position, or any protons in the benzylic position rather. Okay, so you can use NBS and UV light in order to go and replace that proton with a bromide. Very, very, very synthetically useful. Okay, you can go and use that bromide, maybe do an SN2 on it, maybe eliminate it, do whatever you want in order to proceed with your synthesis. Okay, I always recommend that whenever you have a benzene and just an alkyl side chain with no functional groups, one of your first likely steps will likely be either NBS or maybe oxidizing it, which we'll talk about that a little later. Okay, but just remember that benzylic bromination requires at least one benzylic hydrogen. Now, for that big pet peeve that I was mentioning earlier, this is something that I have seen so many times on exams, and it really pains me to take off points for this because it's a very easy mistake that people do. Okay, this does not occur through benzylic bromination. Okay, so I see people writing this a lot on their exam, and then we're forced to take off points for this. This reaction does not work. What reagents would you want to use for that instead?
Br2 and FeBr3.
Very good, Br2, FeBr3. Cool, yeah, so that's pretty much the big review that I had for radical reactions. Later on, I'll be showing a little bit of, or doing a little bit of practice problems with you guys to see how these can be applied. Any questions on these? All right, I'll give you guys like maybe a couple more seconds to copy that down, and then I'll move on to the next topic, which is going to be aromatics, and there is a lot to talk about with that. Well, the kinetic, Matt, what exactly do you mean by the reactivity table?
The table where it's like for each halogen, there's like a first degree, second degree, third degree, and then it's like the ratio is like 1 to like 60 something.
So that reactivity table would only be for like monohalogenation for alkyl groups, right? I think the kinetic product will probably just be based off of the most stable radical, but you actually have multiple contenders for that, which means that you'll probably have multiple potentially kinetically favorable products. So you see that you have like a tertiary radical here and a tertiary radical here. So those would be two likely kinetic products.
Right, thank you.
Mm-hmm. All right, are you ready to move on to the next topic? Okay, next topic is going to be our aromatics, okay? Notice here that there are a lot of different things going on with our aromatics. Particularly, the biggest thing that we're going to discuss is our electrophilic aromatic substitution, right? We know 5 reactions right now that are part of that subset, okay? So that's going to be your nitration, sulfonation, halogenation, and then your 2 Friedel-Crafts reactions. Aside from that, there are two other useful reactions, technically three, but we already talked about one of those, that involve aromatic rings that need to be activated by some sort of a presence of an aromatic ring. That being your oxidation of alkyl benzenes, that's here KMNO4, and also your Sandmeyer reaction, which can take an amine and then form your diazonium ion and replace it with whatever substituent you want. Okay, a little diagram that I have over here, which will be useful in a little bit when I talk about it. But whenever you have a benzene ring with a substituent on it, you have to consider the different types of positions that you can have. So these are just nomenclature right here. So you see O in blue is going to be your ortho position, M is meta, and then P is para. If you want a more numerical representation of it, ortho is just 1, 2 to whatever R you're looking at. Meta is 1, 3. And para is 1, 4. All right, so yeah, that's really important to know. And aromatic reactions can be done with any aromatic ring you want. But right now, you guys see on your back test that Fazon is mostly focusing on benzene. Okay, so it's good to know your criteria for aromaticity. But right now we're going to be talking about benzene. And then later on in the semester, we're actually going to be revisiting aromatic reactions with different aromatic rings, such as pyridines and perols. Okay. So now let's go ahead and then talk a little bit about electrophilic aromatic substitution and the general mechanism for that. Now, electrophilic aromatic substitution is a lot to write. So whenever I'm going to refer to it, I'm going to abbreviate it as EAS. Okay. So a general representation of what an electrophilic aromatic substitution reaction is that you start off with some sort of an aromatic ring like benzene. And you're going to be using some sort of an electrophile, usually activated by a Lewis acid catalyst. And you will in some way, shape, or form be adding that electrophile to your aromatic ring. Okay. Now, if you have to do an electrophilic aromatic substitution mechanism, truth be told, if I can scroll up again, thanks iPad, there we go. These 5 mechanisms are nearly identical, okay? They only really differ in their first step. So that first step I'm gonna tell you right now is going to be the formation of your electrophile. So nitration, sulfonation, halogenation, and your 2 FC reactions, you have to form some sort of an intermediate that will go and then help react. Okay, so let's go ahead and then look at what a general electrophilic aromatic mechanism looks like. So the mechanism can be divided into 3 separate steps. Okay, your first step would be form your electrophile. By reacting your reagents with your Lewis acid catalyst. Now, when I write LA there, that means Lewis acid, not Los Angeles, so don't get confused. Okay. The next step would be to go and temporarily break aromaticity. To attack your electrophile. Okay, that's where you go and then end up with that cation intermediate in the middle of your electrophilic aromatic substitution mechanism. And then your last step would be to go and then use leftover base to quench or to restore aromaticity. And quench any byproducts you have. Okay. Okay, so now let's go ahead and then look at a very generalized example of this, okay? Actually, instead of looking at a generalized example, I'll show you the full mechanism for one of them, and then I'll show you the preparations of the electrophiles for the other ones, okay? So the first one I have on this list is nitration, so I'm gonna go ahead and then talk about the nitration of benzene. All right, so for your nitration, the overall reaction involves taking your benzene ring and then reacting it with two acids at once. Those two acids are going to be nitric acid and sulfuric acid. Doing that will end up giving you a nitro group on your ring, NO2. Okay, so that's how the overall reaction looks like. Let's go and then let's go through each of these three steps and see how we can apply that mechanism. Okay, so your first step would be to go and then form your electrophile by reacting with your Lewis acid catalyst. Okay, so do that like that. So nitric acid looks like this. Okay, notice that nitric acid is neutral, so any charges in the compound should come out to being neutral. And then sulfuric acid will look like this. Right? So what's going to happen is that you're going to go and then form some sort of a good leaving group in order to go and then activate your electrophile. And that's something that's actually going to be happening a lot in each of these reaction mechanisms. So it'll become a very common trend. So we end up seeing that in that first step, we can go and then grab the proton from your acid, and then form your conjugate base of that acid in order to go and then give you this intermediate right here, which is pretty mighty unstable if you ask me, because you have two positive charges next to each other. But the whole point of this is that you are now forming a good leaving group. So now we can go ahead and then push these electrons back down to form an oxygen-nitrogen double bond and kick off water. That will go and then give you your electrophile along with water. And this conjugate base that will not be useful immediately, but it will be useful again at some point. Okay, so the thing that we're going to be taking right on to the next step is going to be this guy. So now that's going to be your electrophile for when we go in and add in benzene. So the second step is going to be to temporarily break your aromaticity to attack your electrophile. You can go and just do that here. So now is when you can go in and introduce benzene into the mix. All right, then afterwards you can go and attack that nitrogen, right? Attack it, and that's actually going to be pretty similar to how you would attack a carbon, like carbon dioxide or something like that. Then send your pi electrons up to oxygen, okay? So at this point, you have gone and then broken aromaticity. And you've gone and then formed this cation in that broken aromatic ring. So that's your second step. The third step, as I wrote up here, is going to be to use your leftover base to go and then restore aromaticity and quench your byproducts. So we can do that by taking this intermediate that we just formed . Okay, there's a proton laying around over here. And then remember that I said that we would come back and use this at some point. Well, we can go and then use it now. Well, we can go ahead and then take this, grab the proton that you see here, and then form your carbon-carbon double bond in order to end up with your nitrated final product. Okay, if you were to draw a mechanism for this, you certainly don't have to divide it into 3 steps like I did here, but I think it's really useful for understanding how this works in the context of your electrophilic aromatic substitution. Okay, and every other mechanism will work the same, or at least for the last 2 steps. Cool. Any questions on that first mechanism? All right, now we're going to go ahead and then look at our sulfonation. So sulfonation requires, once again, benzene, and then 2 equivalents of sulfuric acid. And then sometimes you might see this with heat as well. Okay, in doing that, you're going to end up getting a sulfonated product as you see here. Cool. Now we're going to go, and then this time I'm only going to show you the first step because the other 2 steps are essentially the same after you've generated your electrophile. So now we're going to go and start off by taking our sulfuric acids, and one of those sulfuric acids is actually going to act as an acid, the other is going to act as a base. So let's see how that looks. All right, my bad. This should be sulfonyl here. So to do this, let me actually separate this out right here, like this. So we first want to go and then activate that electrophile by taking your electrons and then grabbing that proton in order to go and then form water, again, a good leaving group. All right, and then similar to how we did before, we end up forming this and our conjugate base. We can actually go and then just kind of kick off that good leaving group. And then we will end up forming this cation on the sulfur, which will end up being your electrophile that ends up being attacked. Okay, so that is pretty much the formation of your electrophile, and then pretty much afterwards, the benzene will come in and donate its electrons, and you would just be using this leftover base in order to go and then restore your aromaticity. Okay, that's sulfonation, and that's the formation of that electrophile. Now the next one I'm going to be doing is going to be bromination or halogenation. Okay, so halogenation so there's 2 different like 2 different ways you can halogenate. You can either do it with bromine or with chlorine. So you can use Br2 and FeBr3 to go and then attach the bromide at that position. You can also use chloride and aluminum trichloride. To go and then end up using getting a chloride as well. Okay, you can also use AlBr3 or FeCl3, but these are the main types that you might see. Okay, now for the first step in forming that electrophile, you're actually going to take, I'm going to draw it for only one of them. So you're going to take the lone pairs from one of your halides. And then the nice thing about these Lewis acid catalysts is that they have an empty p orbital. So you can go and then donate your electron density into that empty p orbital and end up this reactive intermediate that you see here. Okay, now you can consider this bromide over here to have that this bromide really hates having that positive charge. Okay, so if you were to go and then attack that in the next step, you would be able to go and just attack over here and then kick everything else off. Okay, I don't know why. There we go. Yep, so you go and then kick that off as you see there. Okay, so that is how halogenation works. I just gave you like a preview of that second step. And then the other two, Friedel-Crafts alkylation and acylation, are going to be relatively similar in that first step. However, we're going to be seeing a couple different weird things going on with both of them. Okay, so for Friedel-Crafts alkylation, you can then essentially alkylate whatever R group you want on there. Well, not whatever R group you want. There's some exceptions. So you're going to have some sort of an alkyl halide, could be bromide or chloride, doesn't matter, and AlCl3. And the whole purpose is that you're going to be attaching some sort of R group that contains usually only carbons and hydrogens. All right. Now for that electrophile formation step. Okay, so you're going to be doing something very where you have your R group and your chloride.
Is there something else I can help with?
Oh my God. Sorry. I was like, no, you can't help with anything. Sorry, Siri. Okay. Yeah, so you're going to go and attack over here. And once again, you end up with a good leaving group. Okay. Now, it's very worth noting that in most cases, not necessarily all cases, you will be forming a carbocation intermediate out of this. This is because this might leave SN1 style in order to go and then give you some sort of an alkyl cation. Now, I'll leave this at here as just R plus right now because we're actually going to talk about it a little more later when we get to the limitations of these, right? But just know that you're going to have some sort of a cation forming there, or maybe sometimes if you have a much smaller R group, like a methyl group, or if you have a methyl group, you might just end up forming, doing like an SN2 type reaction instead, but that's not too important right now. Okay, the last one is going to be acylation. Actually, before I talk about acylation, I'm going to do a quick honorable mention, if you want to call it. Okay, because there is a type of reaction that's very similar to your Friedel-Crafts alkylation, and that's just going to be using sulfuric acid or hydrofluoric acid in order to go in and alkylate. Okay, so that looks like this. So let's say I have some sort of like an alkene, like cyclohexene. I can use either sulfuric acid or hydrofluoric acid in order to go ahead and then end up alkylating Friedel-Crafts style. Okay, so Friedel-Crafts alkylation works very similar to this, right? Essentially, what's going to end up happening is that you're going to use the acid that you have here in order to form a carbocation from this reagent here. So it's just a matter of a reaction that looks something like this. Okay, so you would use that double bond. Okay, then you would go and then use whatever acid, either sulfuric acid or hydrofluoric acid. They're both non-nucleophilic acids. And then you'd end up forming a cation, which will end up being the electrophile, that you will end up using for the next step. Okay, It's a bit of a lesser known reaction, but it applies the same principles as Friedel-Crafts. Okay, cool. And then the last one, the last reaction, or the last electrophilic aromatic substitution that we have is going to be your Friedel-Crafts acylation. The dog barking outside agrees with me. Okay. I think I cut for a second. All right, yeah. So Friedel-Crafts acylation, very similar to Friedel-Crafts alkylation, where you use similar reaction conditions. There was a dog that barked outside earlier, and I think when the dog barked, it shut off my Wi-Fi for 2 seconds and then made my Apple Pencil run out of battery again. So yeah, for Friedel-Crafts acylation, essentially, unlike alkylation, you're going to be adding in an acyl group. And I'll also cover some misconceptions that people have about this reaction that you need to be very careful when you're doing in synthesis. Okay, so for Friedel-Crafts acylation, and you're going to be using some sort of an acyl halide. With a Lewis acid catalyst in order to give you that final product. Now, will this give me full points on an exam? Am I missing anything here?
You're missing water.
Water, very good. So first step, this, second step, water. Okay, and I'll tell you what that water means in a little bit. Okay, but this is what Friedel-Crafts acylation does. Now, just to let you guys know, be careful with your acyl chloride, right? Because if you try doing this, and I have seen some people try using this before, this is an absolutely terrible electrophile. Chloride, the acyl group and the chloride both have to be on the same carbon. Okay, and my screen froze again for some reason. Come on, there we go. Yeah, it's a terrible electrophile, not an acyl chloride. The reason I know it's a terrible electrophile is that hypothetically, in the reaction mechanism, you would end up getting a cation in this position, right? Which would be bad because it's going to have a hard time forming because it's a cation that's right next to a partial positive. Okay, so do not use this as an electrophile for Friedel-Crafts acylation. Okay, if you find yourself using something like that, just know that it's probably wrong. Okay, so let's go and draw out the mechanism for this. Let me actually push this to the bottom. So step one, you're going to go in and take your acyl halide. You're going to take the lone pair from chlorine, attack there. And once again, you've gone ahead and then formed a very good leaving group. Okay. In this case, you're actually going to want to leave to form a very unstable intermediate, which looks just like this, which is called your acylium ion. Tell either in the vinyl position or on the oxygen, which it's not really happy in either place. But nonetheless, it's still a very good electrophile. Okay, so very good to take note of this. Now, what's that water in the second step for? Well, when you end up forming your final product, up. your oxygen that you end up forming here is actually going to go ahead and then coordinate with your Lewis acid catalyst, right? And that's something that you don't want because you want to try and make sure that everything is nice and quenched. So the addition of water, I'm not going to draw the mechanism because it's not something you guys need to know for this. Right, the addition of water allows you to go and then get this final product or like the quenched ketone, and then at the same time you end up getting some aluminum hydroxide as a byproduct. Okay, just something that you guys should be aware of in general. All right, so these are your 5 electrophilic aromatic substitution mechanisms, okay, or at least like the formation of their electrophiles. Any questions on these? Cool. Now, before I get into reductions related to these, I'm going to quickly go ahead and then talk about the limitations of Friedel-Crafts reactions. So you guys have seen Friedel-Crafts alkylation. You guys have seen Friedel-Crafts acylation. Now we're going to look at some Friedel-Crafts limitations. I always love saying that. Okay, so there are 5 different limitations to Friedel-Crafts reactions. I'll get the first one out of the way because the first one doesn't really apply too much to actual like writing of reactions, but the other ones are pretty applicable. So the first one is to beware of overalkylation. Okay, particularly the big thing that you want to be careful with is if you use benzene and you want to go and then do some sort of a Friedel-Crafts alkylation with like methyl chloride or something like that. Now you end up with toluene. Now toluene right here is more reactive than benzene. Why is it more reactive than benzene?
Because it has
The
an
alkyl is electron donor.
It's electron donating, so that means that it's going to be activating the ring, right? So it's activated and you're not careful with the equivalents that you're using for each, you might actually end up over-alkylating. And I've said this a lot. You guys have heard me say this a lot, but I'll say it again. Or it'll be against your will. You can potentially go and then completely end up substituting the aromatic ring, because the more methyl groups you end up adding, the more reactive it's going to be. That's why you want to be very careful with this. Cool. So in order to prevent overalkylation, use an excess of benzene. Okay, hypothetically, you can maybe use like 99:1 benzene to methyl chloride. Okay, but if you have a lot of benzene, then pretty much all the methyl chloride will just be used on mono substituted benzenes. Cool. There are 4 more limitations. Can anyone name another limitation? These are all actually useful for synthesis, so be careful with these.
Carbocation rearrangements.
Carbocation rearrangements, excellent. They're possible with larger alkyl groups. Okay, so remember that at some point you might end up forming a carbocation. You might end up forming a carbocation intermediate. So like, let's say you have an alkyl halide that looks like this, right? With 4 carbons. Well, remember that at some point you're going to end up getting this intermediate, right? And then this guy can go ahead and then break off. And then give you this primary cation, right? I mean, we don't like primary cations, but we can actually go and then rearrange this to give us a more stable secondary cation. In this particular case, we could do it using a 1,2 hydride shift. Okay, so we can go and then draw a resonance structure for this. Okay, we'll end up with this guy, okay? Totally rearranges against your will, and you're gonna end up getting that nice, more stable secondary cation, right? So remember that I said that, or this is a 1,2 hydride shift, but just in general, just know that hydride, methyl, and alkyl shifts I think I cut off there. Yeah, if you guys are not really sure about what this means, make sure that you guys review your carbocation rearrangements from Orgo 1 because any of them can be useful for this reaction. Okay. All right, what is another, I need to add an extra page in here. What's another possible limitation?
No deactivate.
Right, the reaction can occur with any deactivating groups present on the ring. Okay, so have some sort of a deactivating group present on your aromatic ring, then that's really going to make that reaction much harder to occur, right? Any reaction will be slowed down, but the Friedel-Crafts reactions are so slow and generally like hard to react that they will actually not react if you have any deactivating groups present on your ring. Okay, so let's say I have let's see, like a nitrate, or like let's say I have some sort of like a maybe carbonyl here, something like that. Doing a Friedel-Crafts reaction on either one of these will result in no reaction. So beware of that. All right, two more limitations. What's your next one?
No vinyl chlorides or vinyl halides.
No vinyl halides.
Somebody said that in the chat, by the way.
Ah, cool. Yeah, so for vinyl halides, you want to be very careful. Now, there's another misconception that I want to clarify here because a lot of people tend to get confused between vinyl halides and allyl halides. Okay, vinyl halides are not allowed, but allyl halides are allowed. So let me quickly go ahead and then clarify that. So whenever you have a vinyl halide, okay, that means that your halogen is directly bound to your double bond. Okay. If you try and do that, you'll end up with no reaction possible. Okay, so that's a vinyl halide. But now compare that to an allyl halide. Where I have an extra carbon in between. Okay, in the allyl halides, of course, you need your Lewis acid catalyst with this as well. Reactions like this are totally possible, and they are technically considered monofunctional because of the fact that the carbocation that you end up forming is stabilized via resonance. Okay, so allyl halides are possible. You can use them. Vinyl halides are not possible. Okay. Also, another thing that you can not use, let me squish this in between. Aryl halides or halides bound to aromatic rings, not possible also. So some people might try and do this. you'll also end up with no reaction. Okay, so be very careful with that. Okay, the whole premise is that you do not want to form, you don't want to form an, what's it called? You don't want to form a vinyl carbocation. Okay, those are really highly unstable. But now I have a question for you guys. Is there a way that I can possibly still get this vinyl group here onto this ring?
Yes.
How so?
I'm pretty sure you could do Friedel-Crafts alkylation first and then NBS and HV and then eliminate.
Mm-hmm. So go ahead and then add in 2 carbons first. That won't rearrange because it's too small to rearrange. Okay, then afterwards go and then add in NBS and UV light in order to go and then brominate at your benzylic position. And then finally just go and then top it off with your favorite base, like tert-butoxide. In order to go and then eliminate to give you that final product. Okay, you can also do an acylation and Wittig as well. For exam 2, when you learn about Suzuki and Heck reactions, that's another way that you could potentially go and then do that same transformation. Cool, so that's for 4, and then there's 1 left. Anyone know what that last limitation is?
It's no amine group
Yep.
on the
No amine groups on your ring. Okay, particularly we're looking at if we have something like phenyl. When you go and then you try and react with some sort of a Friedel-Crafts reagent, you actually don't get the Friedel-Crafts reaction. Instead, what ends up happening is that the catalyst will go and then coordinate with that amine. Okay, and then as a result, you have deactivated the ring. Okay, so be careful with that. You cannot have any amine groups on there in order to go and then conduct that reaction. Cool. So of these 5 limitations, which ones do you think also apply to acylations? There's 2.
is it the deactivating groups and the final halide?
What was the second one?
The amine groups?
Yep, that's right. So 3 and 5 over here, both apply to acylation. All right, beautiful. Any other questions on this?
Wouldn't the ethyl chloride for like adding the vinyl halide, wouldn't that go through a carbocation rearrangement?
The ethyl chloride, no, ethyl chloride can't, because if it rearranges, it just goes to another primary. So you can't rearrange from primary to primary.
Okay.
All right, cool. So we do still have a bit of aromatic stuff to talk about. So I'll quickly talk about activating and deactivating groups, and then I'll talk about the reductions, and finally Sandmeyer and oxidation of alkyl benzenes. Don't expect it to take too much time, hopefully. Okay, so then for this, now we're going to go and then look at our directing groups. Okay, so for directing groups, some things to keep in mind is that if you are ortho-para directing, you activate the ring. Meanwhile, if you are meta-directing, you deactivate the ring or make it less reactive. Okay, and then there's 3 different ways that you can actually activate or deactivate a ring. And those 3 ways that you can activate or deactivate a ring are either via resonance, via induction, or via hyperconjugation. Okay, so for these 3 reasons, you want to go ahead and then explore how they could potentially go and then affect the directing of your ring. So I'm going to show an example of each. So let's say I have a phenol, right? Now you can do this by drawing out every single possible resonance structure. That'll take you a very long time. Personally, what I like to do is that I like to take one of these bonds and then push it in 2 different directions and see which one works out better. Okay, so I go in and I try pushing my electrons, let's say in this direction. I end up with a cation and anion in that formation, versus if I draw it in this direction, I end up seeing now that my cation and anion are completely swapped. Okay. So now my question is, now what I want to do is that I want to go and look at the placement of my anion and cation and then see which one is going to be happier, right? Particularly the cation will help you out the most. Now looking at this cation over here, you see that this cation has something that this anion does not. And the cation is stabilized by the resonance of the alcohol group that you have here. Okay, so as a result of that, we can end up saying that this arrangement over here is going to be more favorable because we have that resonance stabilization. We can call this partial positive over here because that's where the more favorable positive charge was. Then we do partial negative, partial positive, partial negative, partial positive, partial negative. Okay, we notice that we have partial negatives on our orthopara positions. So we end up saying that this is going to be orthopara directing. In this case, because the cation is resonance stabilized, it's going to be orthopara directing via resonance. Okay, for an example of induction, in this case, we don't really have to draw resonance structures for this. So like, let's say I have a trifluoromethyl group here. Okay, well, you know that there is a very huge dipole going on over here between the carbon and the fluorine, right? So we could do a partial negative on the fluorine, partial positive on the carbon. And if we know that, we could just go in and continue moving around the ring. So we have a partial negative, partial positive, partial negative, partial positive, partial negative, partial positive. In this case, we see that our partial negatives here are going to be at our meta positions. That means that we could say that this is meta directing. And this is going to be via induction. Okay, now you're probably thinking, wait, Juan, but this cation over here would be tertiary. Yes, I agree that cation is tertiary, but when we're thinking about induction versus hyperconjugation, induction actually takes the cake because we want to make sure that we don't have any conflicting charges that will potentially make one charge unstable. Okay, now for hyperconjugation, like let's say I have some sort of like a methyl group here, for example, I can once again go and maybe try pushing my electrons in 2 different directions. So I will end up getting, life hack, let me actually just copy paste this from here. Instead of a phenol here, I'll just have a methyl group here. Okay, so now when I go and then I draw my resonance structures in either way, then you can see that right here you have a tertiary cation and a secondary anion. Whereas in the other case, you have a tertiary anion and then a secondary cation. Okay. Remember, cations are stabilized by hyperconjugation and anions are destabilized by hyperconjugation. So that makes this one up here more favorable. Knowing that, we could put our partial positive and partial negative on this carbon followed by this carbon and then just go and then move right along. Now we want to look at where our partial negatives are going to be. We have one here, and one here. So that means that this is now going to be orthopara directing. In this case, via hyperconjugation. Okay, so this pretty much proves to you that you don't have to memorize that big list that he gives you, but there will be some cases where you're going to have to go and examine case by case which one is going to be orthopara or meta-directing, and in that case, you could just draw all full resonance structures or work with partial charges as you saw here. Okay, any questions on directing groups? Okay, let's go ahead and quickly talk about reductions. Okay, and then these are, I'm not going to be talking about hydrogen reductions just yet. Instead, we're going to be going ahead and then talking about the reductions that have to do with, or potentially have to do with carbonyls or benzene rings or whatnot. Okay, so I'm going to go and then put out a few examples here. I believe this was either the same or a very similar example that was used in Pilot. I think that Pilot problem is a really great way to go ahead and then review what your reductions are, but we're going to go ahead and review it here anyway. Okay, so let's start off by looking at, let's say H2PDC. So remember that H2PDC wants to go and then reduce two things in particular. Okay, H2PDC will want to go and then reduce the nitro group, and it will only reduce carbonyls if it is in a benzylic position. Okay, in this case, that carbonyl is a benzylic position, so we reduce that, but this one stays the same. Okay, you know what? Just for fun, I'm going to extend this molecule a little bit. I'm going to include another thing. Okay, in addition, it also reduces any carbon-carbon pi bonds into single bonds.
Juan,
Yes.
do you mind explaining why the carbonyl, you might have said this, but I think I missed it. The carbonyl closer to the benzene is reduced first.
It's because it's in the benzylic position. We don't really know exactly what the mechanism is involved, but it's likely some sort of like a radical or a cation that stabilizes it. The other carbonyl just remains.
All right, sounds good. Thank you.
Mm-hmm. So remember, any past use of H2PDC you had will still remain. Okay, so if you had an alkyne there, that would go and then reduce that as well. Let's say I wanted to go and then use Wolff-Kishner. Or let me not write Wolff-Kishner, let me write my. Okay, so these guys right here are, these are my Wolff-Kishner reagents. Okay, so what does Wolff-Kishner do again?
It reduces the carbonyls, both of them.
Yep, so it's going to reduce both carbonyls. So it can reduce any carbonyl into a, oh, what's it called? Yeah, it can reduce any carbonyl into an alkane, regardless of the position. And it leaves the nitro group. Okay, so that's going to be your Wolff-Kishner reduction. Your Clemmensen, and another thing about Wolff-Kishner reduction is that it is in basic conditions. So you want to be aware of any acidic groups that you have there. The other reaction that you have is going to be your Clemmensen reduction. Okay, and then that Clemmensen reduction, that's just with zinc and mercury and hydrochloric acid. it'll go and then do the exact same thing as your Wolff-Kishner reaction did, but now in basic and acidic conditions. You could tell because there's an acid in there. Nothing else is touched. And you end up, once again, removing both of your carbonyls, right? Lastly, we have another one that's a little lesser discussed, but still very useful. And that is tin and hydrochloric acid. Anyone remember what that does?
It reduces-
Nitro specific.
Yep, it is nitro specific. It'll only reduce the nitro group. No, it will reduce that into the amine. Everything else remains. All right, beautiful. Any questions on the reductions? All right, yeah, these are the big reductions that you have with respect to aromatic rings. So make sure that you guys review them because they're very useful for synthesis. Okay, quickly gonna go ahead and then talk about oxidation of alkyl side chains, and then finally Sandmeyer, and then we can move on to carbonyls and epoxides. Hopefully, I'm hoping that we have some time at the end to do like a quick like synthesis practice or something. Oxidation of alkyl benzenes. All right. So for our oxidation of alkyl benzenes, this has a very similar requirement to our benzylic bromination, okay? In the sense that you will need at least one benzylic hydrogen. Okay, so if we require a benzylic hydrogen, that means that if you don't have it, then the reaction will not occur. So what happens is that you can take a set of oxidizing agents, very strong oxidizing agents. So the big one is potassium permanganate with sulfuric acid and heat. What's going to happen is that it's going to leave everything past the, or pretty much past the benzylic position. Okay, and you're just going to end up with a carboxylic acid at the benzylic position. Okay, so you're pretty much, the product will always look the same if you have a benzylic hydrogen. Now, if you do not have a benzylic hydrogen, like this, if you were to go ahead and then try and conduct this reaction, you'll end up with no reaction. Okay, so that benzylic hydrogen is very, very important for this. Okay, you might also see this reaction with H2Cr2O7 rather than KMNO4. Okay, so just be ready to see that in case that comes up. Cool. Mechanism, we don't know. What happens to the rest of the carbon chain, we don't know. All it knows that you will end up with a benzylic carboxylic acid.
And that one is different from Jones, correct? Then like the H2Cr2O7.
Yes, Jones goes and then oxidizes primary alcohols into carboxylic acids or secondary alcohols into ketones. So we'll see that later. Well, any questions about oxidation of alkyl benzenes? All right, and then last one is Sandmeyer. Okay, now for your Sandmeyer reaction, you need to start off with some sort of an amine, right? So a phenylamine. And you're going to do a couple things. First, you're going to go in and react it with sodium nitrate and hydrochloric acid at 0 degrees Celsius. Okay, there's some acid-base reactions going on there, so 0 degrees Celsius is very important. And then you end up with your diazonium ion. Okay, and then what's nice is that you can use this diazonium ion, which goes and then forms a very unstable phenylcation, and you can go and then replace it with whatever other intermediates you want. Okay, so some common examples of these are, let's say you were to go and use copper bromide. You can go and then replace it with a bromine, which you might be asking, wait, Juan, that's probably not useful if I already have Br2 and FeBr3. If you need, or like if you have some sort of like meta directing thing going on where you can't use the Br2 and FeBr3, then this is especially useful. Okay. Another possibility is if you wanted to maybe add in an iodine, you can use potassium iodide. Okay, probably the most common one that you're going to be seeing is if you were to use copper cyanide, you end up with a phenylnitrile. And then another one that you might potentially see is if you were to use some sort of aqueous sulfuric acid. I know I've seen variants of this. You can end up with a phenol. Okay, I know I have seen copper 2 oxide being used for that as well. Really, any of those reagents works. Okay, these are the most common versions of each that I've seen. Ooh. All right, that is Sandmeyer. And the last, I have to talk about aromatics before we move on to carbonyls and epoxides. Okay, any questions on this? All right, full speed ahead. We will now be going to what we're going to be talking about for the rest of this review session, which is going to be your reactions of carbonyls and epoxides. Okay, there are a lot of different things to consider. Okay, I'm going to be touching upon a lot of these, but these are things that you do want to be considering when you're drawing a mechanism, when you're going and when you're going and maybe like conducting a synthesis. Okay, so let's go ahead and start off by talking a little bit about acidic and versus basic conditions. So for acidic conditions, essentially you want to make sure that you have no cations in solution. Sorry, no anions in solution, not cations. Or net negative in solution. Okay, and then what you're going to notice about acidic conditions is that the first step will be to go in and protonate your oxygen on the epoxide or the carbonyl. Okay, so some generic examples of how these mechanisms might look like. So let's say if I have a carbonyl, including an aldehyde or a ketone, and I want to go and then bring in some sort of if I'm working in acidic conditions, my first step will essentially always be to go and then protonate in order to give myself this activated carbonyl. Then usually you're going to go and then have some sort of a protonated nucleophile. It's important to note that it'll be protonated because you'll need to deprotonate it to make it neutral. Where essentially you'll go and then attack to form some sort of an intermediate like this. Okay, then at some point you'll get some sort of a conjugate base. Actually, I'll just leave it here because some of these mechanisms might end up like a little differently, and as you'll see when I draw up the mechanisms for everything else. Okay, but for epoxides, you will also go and then protonate that oxygen first to Lewis acid to go in and catalyze it there, right? Then afterwards, we're going to be considering the stability of the transition state. So secondary partial positive transition state is going to be more stable than a primary partial positive transition state. So we can go and take our protonated nucleophile. And then attack over here. Then note that when it's neutral, it goes and then attacks over here and it becomes positively charged. And then you would just take whatever base you have left over in solution. Maybe it could be some leftover solvent, but that will essentially come in and then deprotonate. And that's typically what a reaction in acidic conditions will look like for both carbonyls and epoxides. Okay. For basic conditions, on the other hand, requirements are pretty much the opposite. Where you have no cations or net positives in solution. Okay, essentially, you actually will start off by attacking right away, but usually basic condition mechanisms will require an acid workup in the second step. Okay, so let's look at some generic format as to like how it might potentially look like. Okay, so for attacking a carbonyl, you might expect that your nucleophile is negatively charged and it'll come in and then attack over here at your carbonyl in order to go and then give you this negatively charged intermediate. Then in the second step, you would be adding in something like acid water, which will essentially come in and then quench in order to go and then provide you with your final product. Okay. As for epoxide breaking, we're no longer dealing with partial positive transition states because we're in basic conditions. But now essentially what you should know with this is that you want to go in and break at the least hindered side. So like this. You end up with the anion. Then afterwards, you will go ahead and then protonate in order to give you your final products. Okay, so note the differences in regioselectivity here, and note that in both cases with epoxides, I've stressed this a few times already, or in the past, if you've talked to me, but notice that epoxide breaking always results in a 1-2 relationship between your newly formed alcohol and your nucleophile. Very useful for when you're looking at synthesis. Now let's go ahead and then look at some of the reactions that you're going to be looking at for this exam, along with some synthesis applications, and see how their mechanisms look like with respect to what I've drawn here. Okay, that's just a nice little introduction. Okay, I know I just wrote a lot, so I'll give you guys like about a few more seconds to copy things down. In the meantime, does anyone have any questions?
What's your favorite animal, Juan?
I think sharks are pretty cool.
Not sharks.
Actually, no, I didn't have to agree with Sam on that one. I don't know. I guess. I think dogs are pretty cool. Yes, actually, I agree. Corgi is the right answer. I just said that to make Sam happy. Yeah, if we were doing this in session, I would bring in my friends Kuma. I don't know if you guys have ever like seen Kuma or follow Kuma on Instagram, but it's literally the cutest corgi ever. Don't at me. All right, cool. Listen, there are a lot of animals in this world are great. Okay, don't what's it called? Don't put pressure on me. All right, let's go ahead and look at our mechanisms. So a lot of the first mechanisms that you guys saw were actually in acidic conditions. So you see that we start off a lot in acidic conditions and we'll move right along into basic conditions, right? So the first big mechanism we saw was the formation of hydrates. Okay, so a hydrate is just a gem diol, meaning it is a two alcohols on the same carbon. Okay, so we start off with a ketone or an aldehyde. Okay, I mean, just imply that this is a ketone or an aldehyde, right? I'm not going to draw an aldehyde because apparently drawing H's is too much for me. All right, so let's go and I'll show you guys the overall reaction. So the overall reaction is using water and acid, and that gives you this gem diol product here. Okay, your mechanism starts off, of course, because it's in acidic conditions, you go and then protonate your alcohol, or your oxygen, and then you go in and then bring in your water to attack and form your tetrahedral intermediate, which is just protonated. And then finally, you go in and then bring in some extra water. The reason why it's okay to use extra water is because water is probably proton. Now, one thing you guys might not know is that hydrates actually exist in equilibrium with your ketone or aldehyde. However, one carbon oxygen double bond is actually stronger than two carbon oxygen single bonds. So we do observe some equilibrium actually more shifted towards the starting material. Okay, so something you guys should be aware of, but still a mechanism that you guys should know. Okay. So now let's go ahead and look at our next one, which is very similar, but it's a little longer. And that's going to be our formation of acetals and ketals, also in acidic conditions. So instead of bringing in water, you're going to bring in an alcohol. So let's do let's say ROH here. And you're going to bring in some sort of acid as well. So you're going to end up with an acetal or a ketal. So the big difference between acetals and ketals is that if your starting material was an aldehyde, you end up with an acetal. If your starting material was a ketone, you end up with a ketal. So let's go ahead and then check out how that mechanism looks like. So right off the bat, I'm going to be lazy and tell you that this first step of the first reaction is exactly the same. Because we're in acidic conditions, we need to go and then protonate our carbonyl first. Now, instead of our water attacking this time, it's actually going to be our alcohol solvent. So we go and then attack here, and then the electrons are sent up, as you see there. And then you're going to end up with this intermediate here. Right, and then now, again, we're not really assuming any water in here, but let's say that because your alcohol is your solvent, you have a ton of it in solution, you can go and then grab this over here in order to go and then end up with your net neutral intermediate. All right, then with that net neutral intermediate, that's either going to be, or depending on what we started with, it's either a hemiacetal, or in the case that I drew, a hemiketal. All right, but we don't actually stop there because we still do have a lot of acid and we have a lot of acid and solvent left in solution. So we actually need to go and continue. So we're going to go and then continue deprotonating over here. and we're going to end up with water, which, as you know, is your good leaving group. Now, hypothetically, you could protonate either one of these, but if you protonated this guy, you would just be doing the reverse reaction, which would be very counterproductive for how much we're doing here. Okay, so we go and then protonate this, and then in order to kick off our good leaving group, we have to reform our carbon-oxygen double bond. So we go ahead and just do that in order to give us this protonated intermediate. Now we have to keep going. So now that alcohol solvent is going to once again come in and then attack, sending our electrons up. And then giving us this protonated intermediate. We're almost done. But afterwards, we can go and sorry, that was my roommate coughing. I don't know if you guys heard it, but well, we go and then end up with this final product that we see here. Okay, so this here is now your acetal or your ketal, depending on what you had. Cool. Now, like any good organic chemistry reaction, there are some applications of this, which I won't have time to draw the mechanism, or maybe I won't have time to draw the mechanisms for these now, maybe later if we have time. But some of the extra reactions that you guys have to consider. One of them is protecting groups. Oop. Apple Pencil really not cooperating with me today. I say it's not cooperating with me, but it's really just my fault for not charging it before. Okay, so two things that I'm going to be drawing now are going to be the formation of, or the use of protecting groups in order to go and then form, or like, you know, those like masks that you see there, and also intramolecular acetal and ketal formations. Okay, so there are specific mechanisms for these. They show up a lot on back tests. If I don't get the chance to draw it today by the end of the review session, I do recommend that you go into your back tests and try drawing them out, okay? Not gonna lie, the mechanisms are pretty similar to what you have here, just, you know, with the application that you actually need to involve some sort of an alcohol group from within the molecule. Okay, so I recommend you guys practicing those on your own because those will tend to come up a lot on exams. Okay, all right, Apple Pencil should be good now. So with protecting groups, you want to bring in some sort of a diol, an acid, okay? And we end up getting a compound that looks like this, okay? So that's your protecting group for your ketones and aldehydes, okay? I always like to highlight these in case you guys don't really see where everything is. So this would just be this guy right here, and then this would just be this guy right here, okay? This can actually be very easily collapsed with just acid water. Okay, and this reaction is also reversible as well. Okay, so you can actually go and then reverse this reaction by using acid water in order to go and then give you back your final ketone. Okay. Another application. Okay, 1, 2, 3, 4, 5. Let's say I went ahead and used, let's see, methanol, for example, and acid. Okay. Essentially, what would happen with this? I guess since this shows up on a lot of exams, I'll just quickly draw the mechanism for the intramolecular one. But essentially what happens is that you're going to go ahead and protonate this guy. So you go ahead and then end up with this protonated intermediate. Then afterwards, you want to go ahead and then swing this guy right over, and you're going to end up forming a 1, 2, 3, 4, 5-membered ring. You go and then send your electrons up over here. So your 5-membered ring ends up looking like this, right? For time, I'm actually going, I'm not like, do draw the protonation and deprotonation steps if he asks you to. But for time, I'm actually just going to go ahead and then draw minus H plus and then plus H plus. Have you guys seen Dr. Falzone use this notation before?
I personally have, I was in Greenberg last semester.
So essentially what this is just signifying the removal of a proton and then the addition of a proton somewhere else, okay? You're gonna see Falzone using it a lot more often. I'm using this right now just for the sake of time, but you're essentially going to be deprotonating and then reprotonating somewhere else. That's the significance of that. So then here you would be going and then forming a good leaving group, right? Then afterwards you go and then form your carbon-oxygen double bond to remove said leaving group. Right, and then you end up with this oxyanion intermediate, which is now when your methanol comes in and attacks. And then send your electrons up like that. Right, so then you end up with an intermediate that looks like this. And then finally, to top things all off, you would just want to go and then maybe use excess methanol solvent. Final product. Cool. This is a mechanism that people do tend to get stuck on, so be very, very careful with how you draw this. Okay. Any questions about these mechanisms? Okay, now let's go and then talk about two other reactions that occur in moderately acidic conditions, right? So these are going to be your formations of amines and imines. Okay, so sorry, imines and enamines, my bad. All right, so for your imine formation, essentially what you're going to do is that you're going to take some sort of an aldehyde or a ketone, and you want to react it with a primary amine, okay? A primary amine is just an amine that's bound to one carbon, one R group. So like RNH2, for example. And you want to use some sort of like a trace acid, such as like maybe concentrated trace hydrochloric acid or something like that. Okay, your final product will end up being this imine that you see right here. Basically, you have a carbon nitrogen double bond. Cool. Now, the thing with this reaction and the next reaction that you see here is that it's going to occur at a pH of approximately 4. Okay, so not too acidic and definitely not basic, right? You want to have a pH of 4 to allow your amine to not get protonated. By a strong acid, which allows the reaction to occur pretty much. But at the same time, it still allows for the protonation of the tetrahedral intermediate. Okay, THI just means tetrahedral intermediate. Okay, So now for the mechanism, even though we have moderately acidic conditions, we actually don't want to protonate right away because that would actually sacrifice our amine. So we would start off with our amine and we would attack straight away. Okay, so attacking straight away like this ends up giving us this intermediate. This is a type of intermediate that's called a zwitterion. Zwitterion just means that you have two different functional groups on the compound that have different formal charges. Okay. Now this, once you come in and then attack, is where your trace hydrochloric acid is going to come in and then deprotonate. So it's going to go and get deprotonated by the oxyanion to give you a neutral alcohol. After this, though, the chloride will now come in and then deprotonate your amine. In order to give you this net neutral intermediate that you see here. Okay. Now, once you do that, you want to go and then protonate your alcohol. Okay, and then similar to how we kicked off good leaving groups before, you want to go and then reform the carbonyl that we have here, or reform the imine in this case. Kick off your water. Then you end up with your protonated imine, which can just go ahead and get deprotonated by your leftover conjugate base of your hydrochloric acid. And we have gone ahead and then formed our imine. Okay, so that's how our imine looks like. Our enamine formation. So enamine is a different functional group, but the mechanism is virtually the same except for the very last step. Okay, so for that enamine formation, so you start off with ketone or aldehyde, but now instead of using a primary amine, you're going to be using a secondary amine. And the product ends up looking more like this instead. The reason why it looks like this, like the amine earlier, is because you deprotonate in that very last acidic proton on the amine. So you have to go in and look for the next best thing. Okay, don't freeze now. Okay, so that's how the enamine looks like all the way there at the bottom. Now the mechanism will look the same. So from where you start, I'm not going to draw the whole mechanism just because it'll be a little redundant. Right, so you end up with this. So you start off with this intermediate. Ends up with this zwitterionic intermediate, and then essentially you will do the exact same thing for everything until you end up at this point of the mechanism. Right, so here you would go, and then similar to what we did above, let me make these the right colors. Similar to what we did above, we would go and then kick off our water. Right, and then when we kick off that water, we now have this positively charged intermediate, right? Now we can't just deprotonate in our group. That's not how it works. But we do have a nice and acidic proton over here that we can go and then deprotonate. minus that we have here. Grab this proton. Is it lagging behind me? There we go. Yeah, you go ahead. Form your carbon-carbon double bonds there. And then send your electrons up in order to give you that final net neutral enamine. So this is how the mechanism for both amine and enamine formation works. Cool. Any questions on these? All right, so now let's go ahead and start moving more into the basic territory. We're going to start off with a very weakly basic reaction. And this is going to be our cyanohydrin formation. Okay, so for our cyanohydrin formation, there are many different ways that you can see this represented. I know that I've seen the case of where you have KCN in the first step and H3O plus in the second step. One common way that I've seen it, and the one that I probably like the most, is using KCN and HCN. Okay, using KCN and HCN will go in and give you the cyanohydrin, as you see here, having an alcohol and a nitrile all in one step. Okay. Now, luckily, the basic mechanisms are a little easier than the acidic mechanisms. So we can go ahead and then look at these easier. So this doesn't require any activation right off the bat because we're working in basic conditions. So we can go and then take the lone pair from the nitrile and attack over here in order to end up with your oxyanion. Afterwards, you can go ahead and then use the very weakly acidic HCN in order to go and then end up forming your cyanohydrin. So everything here is not too basic, not too acidic, so it's a slow but also moderate reaction. Cool, and that is your first reaction under basic conditions, and technically the only reaction that doesn't require an acid workup. And the reason I discourage against an H3O plus acid workup is for a reason that you'll be seeing down 2, where you can hydrolyze a nitrile into a carboxylic acid by accident. So that's your cyanohydrin formation. Now let's go ahead and then look at our hydride reagents and our, let's go ahead and look at our hydride reagents and then also our Grignard reagents. Okay, so you'll be seeing many different types of hydride reductions throughout this semester, but the one that we're going to be seeing right now is sodium borohydride. So this is the first one that I've talked about today that officially requires an acid workup step. Okay, this essentially what it's going to do is that it's going to add a hydride right into the middle. I'll show you guys the mechanism in a bit. But essentially, all you end up getting is an alcohol from where that ketone or aldehyde used to be. For this, you can also use LaAlH4, although it's much more dangerous, just in real life, not on paper.
Are there any reactions that are going to be on this exam that require LiAlH4 rather than NABH4, like the esters and so on?
Not for this exam, but for exam 2, yes. Cool. So for this reaction, you can use your borohydride right here. You're essentially going to go and then break that boron hydrogen bond or boron hydride bond in order to go and then attack here. Right, you go and then end up adding that hydride in that position. And then afterwards, you can go and then quench that with acid. And that ends up giving you this final product. Cool. So that's your hydride reduction. And then next up, your Grignard reaction ends up. Yeah, your next reaction will end up being your Grignard reaction. So there's actually two parts to the Grignard reaction that I want to talk about. The first is your formation of your Grignard reagent. Okay, so the Grignard reagent. So essentially what's going to happen is that you're going to have an R group attached to a bromide. And then you're going to use magnesium and diethyl ether. And what happens is that the magnesium will actually go in and then insert itself in between the R group and the bromide. So then that is a synthesis of your Grignard reagent. Okay, nice and easy. You don't really have to know the mechanism for that. Okay. Now, for the actual reaction itself, what happens is that you're going to take a ketone or an aldehyde. Grignard's going to work differently for different types of carbonyls, FYI. But for ketones and aldehydes, it works the same, where you can go and then take some sort of an alkyl magnesium bromide. Okay, make sure that your R group only contains carbons and hydrogens. Okay, and essentially what's going to happen is that R group will attack in a very similar style to how the hydride did in the hydride reduction. Okay, so essentially there is a transition state, but Dr. Falzone, I believe, does not require you to know that, so I'm not going to go over that transition state. So you go in and attack, and then you end up with an oxyanion in R group. Okay, then afterwards, you can go in and take that oxyanion and then attack in order to give you your final quenched product. Okay, and that is your Grignard reaction. Both steps of the Grignard reaction are very, very important, including the synthesis of the Grignard reagent. So make sure that you guys are familiarized with that. Cool. I think before I talk about direct and conjugate addition, I think the last two I have left are Wittig and Baeyer-Villiger. Okay, so I'm going to go ahead and talk about those.
Could you talk about Grignard reactions and epoxides real quick?
Sure. I mean, Grignard reactions on epoxides is just the same as any basic reaction on epoxide. So remember, your Grignard reagent is very basic. Okay, this guy has a pKa of roughly 55. And then what's going to happen is that you're going to go and then break this coordination right here. You're going to attack at the least hindered side because it's basic. Okay. And then finally, you can go and then do an acid quench.
Thanks, Juan.
Yeah, no problem. Cool. Other questions on this? Okay, let's go ahead and talk about Wittig.
Oh, can you scroll back up again real quick?
Sure.
Thanks. Sorry. Okay, cool. Thank you.
All right, so for your Wittig reaction, again, this has two separate steps. So you have the formation of your phosphonium ylide. And then the actual reaction itself. Okay, so for the formation of the ylide, the way that that works is that you want to take some sort of an alkyl halide, and then you're going to have two separate steps involved with this. The first is going to be triphenylphosphine. Second step is going to be N-butyl lithium, where the N represents the long chain of the butyl, right? So it's like a long constitutional isomer. Okay, doing that will end up giving you a phosphonium ylide that looks like this. As for the mechanism, the first step, by the way, I should also note that this carbon over here should be primary always. So for the first step, you want to go and then attack over here in order to go and then end up with your triphenylphosphine substituted. Please note that triphenylphosphine is neutral when you attack. So it now becomes positively charged and then coordinates with the bromide. And then your N-butyl lithium will essentially come in and then deprotonate right here in order to go and then form your phosphonium ylide. Okay, that goes and then makes that carbon phosphorus double bond, or you can also have the resonance structure where you have a carbanion. Okay, either one is fine. But that's your phosphonium ylide, and now you want to go and then take that into the reaction with your ketone or aldehyde itself. Okay, so let's say I want to go ahead and then do this reaction. What we end up observing simply is that this oxygen and this R group will go and then kind of just trade places. Really, that's the whole premise of the reaction itself. But of course, with that reaction, you have to know the mechanism as well. Okay, so you have it's always good to go and then kind of like coordinate these together. All right, and then you see that essentially what will happen is that this group will come down here and then this will come up here in order to form your oxophosphatane or box intermediate, whatever you want to call it. And you want to go and then repeat the process. Same arrows in the same direction in order to go and then end up with your final product. So that with the R group and then your oxophosphatane. Cool, and then I will also note that your product is usually cis unless it's conjugated. So if you have some conjugated groups or you have some bulky groups on there, then that will potentially go and then favor the more stable products, okay? So otherwise, if you don't have that conjugation going on, like you saw in lecture, then it'll be cis rather than trans. Cool, that's the Wittig reaction. Now let me quickly talk about the Baeyer-Villiger reaction, and I will say a few brief words about direct and conjugate addition. All right, so for Baeyer-Villiger oxidation, you can either do this to ketones or aldehydes with slightly different outcomes with the same mechanism. So you can use some sort of a peracid for this, like MCPBA, or any other peracid. But if you start off with a ketone, you will end up with an ester, okay? And likewise, if you start off with an aldehyde, you will end up with a carboxylic acid. All right, so ketone to ester, and then aldehyde to carboxylic acid. All right, so for to go from your ketone to your ester, essentially, you are going to be going and migrating the larger group. And then here you go and then migrate the hydrogen. Okay, so to do this, what you want to do is that you want to start off with, I'll do the one with the ketone. Start off with a ketone and then protonate using your peroxy acid. Then you end up with this protonated intermediate where you can go ahead and then add in that deprotonated peroxy acid. All right, and then you'll end up with your intermediate, which looks like this. All right, then what's going to happen is that you observe a 1,2 alkyl shift or hydride shift. Remember, your larger group is going to migrate, break that weak oxygen-oxygen bond, and then keep moving your arrows around until you end up with your final ester product. And a carboxylic acid byproduct. Okay, and that is your Baeyer-Villiger oxidation. Okay. Yeah, any questions about this? All right, I have 0 minutes left. If you want to go, you can go. I think I'll spend maybe 2 or 3 extra minutes talking about direct and conjugation. We'll all these reactions this way. I'm sure you attend your. So,
Juan, we can't hear any of that. I don't know if that was just me, but that was just like illegible. But if you need to go, feel free to go. We'll post a recording with like the last 5 minutes on there. If you want to hang around, feel free to hang around and we'll continue. Give it a second, Juan.
Yeah, I won't keep you guys here past like 5 minutes. I'll just quickly talk about the premise of direct and conjugate addition.
Juan, could you please scroll up a bit again?
Yes.
Thank you.
Okay, so
Wait, real quick before too many people leave, I have an extra P set I made for over the summer. I'm just gonna put in the chat real quick. It's just on carbonyl stuff. Sam's gonna send out the answer key afterwards with this recording. But just try it if you want. It's extra practice.
cool. So yeah, for direct and conjugate addition, we do this with alpha beta unsaturated carbonyls. Okay, and the whole driving force behind that is the fact that you have some partial charges over here. Okay, so you have partial negative, partial positive, partial negative, partial positive there, based off of the electronegativity of oxygen. Okay, so then for this, we have a bit of a numbering system here. So we'll call this 1, 2, 3, 4. So we have two different types of nucleophiles that we can use for this. One of them is going to be hard nucleophiles, which are strong bases. They add direct. They're through 1,2 addition. Okay, so your hard nucleophiles consist of things like your hydride reagents, any sort of of alkyl anion, right? So your Grignard reagent, your organolithium. Okay, you have other things such as your Wittig reagent. Or let me. Okay, and then some others that you'll be seeing throughout the rest of the semester. For your soft nucleophiles, these are your weak bases. And then they add a conjugate, which is 1,4. Okay, so some examples of these are going to be things like water or hydroxide, your amines, okay, your nitriles, and something new, your Gilman reagents. Cool. So again, just like a non-comprehensive list, but these are things that you guys should be keeping in mind, right? Now, I will stop by drawing a sample of the mechanisms for both. Very similar, but there are some things to keep in mind for both, okay? So for direct addition, the mechanism is as follows. Okay, so let's say I start off with my alpha beta unsaturated carbonyl. I will use some sort of a hard nucleophile here. The 1,2 position. Okay, the whole naming or the whole numbering between 1, 2 just comes from just by attacking one carbon away. Afterwards, you will end up with this intermediate. And then finally, you would go and then quench.
I don't know if it's just me, but I can't really see your screen moving.
I'm going so fast that I'm not even looking at how laggy my screen is. You know what it is that I tried asking my building to fix my Wi-Fi for like months now, and they haven't done anything. There we go. Yep, do that, and then you're going to end up with your final product. Right, so notice here that in this final product, you've lost your carbonyl, but your carbon-carbon double bond is maintained. Okay, so that's your direct addition. And then likewise, your conjugate addition, last thing for today. Okay, so for your conjugate addition, instead of attacking 1, 2, you'll be attacking 1, 4. So if I start off with my carbonyl carbon 1, 2, 3, 4, I walk around, I want to go ahead and then add in my nucleophile. I add to the 4 position, send my electrons this way, activate the carbonyl once again. I end up with this intermediate with the nucleophile added. All right, and then again, second step acid quench, because these are reactions technically in basic conditions. we want to go ahead and then reform our carbonyl. Our proton adds to our 3 position. And we're going to end up with this final product. Okay, our nucleophile has added to our 4 position. And then notice that we have maintained our carbonyl. And we have lost our carbon-carbon bond. Cool. So yeah, make sure that because these are reactions in basic conditions, you will always, you want to make sure that you are following with an acid quench if you can. Okay, or most of these reactions are. So make sure to follow with an acid quench when necessary. All right, I'm done. I know you guys, your brains are fried. My brain is fried too. I wrote 12 pages of notes straight and I went 8 minutes over time, partially because of technology. Cool. I hope you guys found this helpful. Remember, Sam will be posting the recording soon after this review session, so be on the lookout for that if you missed anything. Make sure you guys get a good night's rest, and we hope to see you in pilot or learning then, and good luck on your exam on Thursday.
Thanks, Juan.
Thanks, Juan.